Thank you very much for the introduction. I'm Donghyun Lim, and this is a collaborative work with Svetlana Silvanova and Martin Ziegler. We particularly thank Akitoshi Kawamura and Florian Steinberg for helpful advice and feedback, and we thank for the organizers to give the opportunity to give a talk here. So first, I'm going to give you some introduction, and I will tell you about I will explain what R21 space is and its piecewise representation, and I'm going to tell again about a small R21 space and its Fourier coefficient representation, and we'll finally look into some perspectives of this work. So the title of this talk is Complexity and Coding Theory of Hilbert Spaces. And there's this fact that every infinite dimensional set proper Hilbert spaces are isomorphic, and this is the Hilbert space. R2, large R2 is a space of all square integrable functions defined on the unit interval, and the inner product is defined in terms of the integration from 0 to 1. And there's an orthonormal basis of this space. This is this. So this is the Hilbert space, and we are interested in a compact subset of this Hilbert space. So let me give you some preliminary notions of some computable analysis. And entropy is a measure, it is a characterization of the space, but in terms of the how complicated the space is, or how big the space is. It is defined as a function from natural numbers to natural numbers. So if you fix some radius, you can cover the space by balls with that radius, and as the radius decreases, you need more and more balls to increase to cover the space. This is defined as the entropy as the function from the radius size and the number of balls needed to cover the space. And as an example, the unit interval has this linear entropy, and it's kind of fairly slowly growing entropy, but for some more complicated space like the set space of one Lipschitz function from unit interval, the unit interval, this space has this exponential entropy. Intuitively, the space of unit interval and the space of one Lipschitz functions. The space of one Lipschitz functions feels much more complicated. So it has some much larger or fast growing entropy. So this entropy captures our intuitive notion of the complicatedness of the space and the modulus of continuity. So here in this function, some consider these as functions, but some of them are discontinuous and some of them are continuous. But even among the continuous functions, some of them are these are more continuous and these are less continuous, and these two are almost discontinuous. And modulus of continuity is a measure of it's a notion of measuring how discontinuous a function is. This is also defined using this equation as a function from natural numbers to natural numbers. And we have we are interested in the modulus of continuity of representation. So when it comes to representation, modulus of continuity somehow captures the idea of how many bits do we need to for this precision, or how many bits do we need to include a specific amount of information. Thus we have this dyadic representation and signed binary representation. So, and it turns out the dyadic representation has squared modulus of continuity, quadratic modulus of continuity, and signed binary representation has linear modulus of continuity. So in some sense, signed binary representation is more efficient than dyadic representation. But we are interested in this: is this signed binary representation as efficient as it can be? Is it some sense optimal? Could we find, maybe we could find a representation that is asymptotically more asymptotically more optimal, more efficient than this representation, but it turns out it is not. This is because of this Steinberg's lemma. This is for this applies to the two metric spaces and a surjective function, and we are interested in the modulus of this f. So for this surjection and its modulus, and they being the entropy, the etas being the entropy, then we have this inequality, and this establishes some lower bound on the modulus of continuity. And because of this lower bound, we could say that actually, because of this lower, so this signed binary representation, the representation for the unit interval has the lower bound, the linear lower bound. So we could say that because of this Steinberg's lemma, the signed binary representation is actually optimal in terms of its asymptotic growth of modulus of continuity. And here we want to do something similar. This is a representation from this Cantor space to the unit interval, but we want to do something similar, and we want to establish some optimality for other representations. So this is the Weierhoff type representation, and the encoding space is the Cantor space, and this is the Kawamura style representation. The encoding space is the string. We encode an element as a string predicate, a partial function from strings to strings. And here in this work, we adopt this string predicate representation. This is not a string function, but a string predicate. And here we define metric in this domain, in this space. So according to this equation defining the distance, the two string predicates are close if they agree on all strings up to some length. So maybe let's observe this formula for a little while. Okay. And as an example, let's consider the standard representation of one Lipschitz function from the unit interval to the unit interval. This is mapped in. This is a representation using the encoding space of string predicates. And in this representation, we encode three informations like the n, and j, and a. And because n is the precision parameter, here we use the supremum suppose that this is the supremum. N is the precision parameter, and a is the value of the input argument of the function that we want to encode, and j is the bit position in because this is a string, not a string function but a string predicate. We need additional argument like j. And this space is compact. The space of Lipschitz functions is compact according to Ascoli. And this representation, like in the case of the signed binary representation, this representation has a linear modulus. and here n and j are encoded in unary and a is encoded in binary, and the reason is that if we do this, a has to be encoded in binary to ensure linear modulus, and n and j do not have to be encoded in binary to ensure linear modulus, and they have to be encoded in unary to ensure some polynomial time computability. And this modulus is asymptotically optimal by Steinbach's lemma, because this one and these two spaces have both of them have exponential entropy. And here we use string predicates, not the string functions, and this eliminates the need for second order complexity. The notion of complexity that you adopt in this work is uh, just the usual notion of complexity, the type 2 complexity, not the second order. And with respect to this representation, the application functional is polynomial time computable as shown by Kawamura in 2012. And actually this polynomial time computability of application functional is the exact characterization of or equivalent representations. A representation delta of research function is polynomial time computable, polynomial time reducible to the standard representation if and only if it makes the application functional polynomial time computable. In my talk. I have given you the introduction, and now I'm going to introduce you to the L21 space and piecewise representation. I already explained you what L2 space is, and this is a L21 space is a compact subset of L2 space satisfying these conditions. So the norm has to be less than or equal to 0, and there's this additional condition. This is kind of a sensitivity condition. So the tau is the cyclic shift operation. So if there's this original function and you just shift it a little bit, then there's this red area. That's kind of the difference. And the intuition for this condition is that if you shift only a little bit, this area, actually this is a kind of the squared area of this one, and the area, the figure calculated by the formula is small enough. So this is the intuition of the second condition, and if we have these two conditions, we know that this space is actually compact. And the piecewise representation of large L2 is defined in this way using the string predicate in a similar manner. N is the precision parameter, J is the just bit position. With J exists because we are not doing this with the string function representation, but string predicate representation. And similarly, the A here this function, these are just square integral functions, and this may not necessarily be continuous. So given some interval, a is the interval index, and if we use the integration to calculate the average, and that's what this encoding, this is what the representation encodes. And similar representation have been used for computability investigations, and we want to do this for complexity theory. And entropy and modulus are also part of complexity investigations, and we show it. And this piecewise representation as linear modulus of continuity, and by Steinbach's lemma, this is optimal. And we have this theorem under piecewise representation. The functional of computing f, and if we get retrieved on f and computing the integral from 0 to 1, this would not be polynomial time computable but exponential time computable. Exponential time computability, we can show that by just brute force algorithm, and for non-polynomial time computability, we could show that it is because basically this functional has to access exponentially many intervals to know this integral, and this can be made formal by perturbation argument. And our conjecture is that under piecewise representation, the pointwise operator, this given two functions, the pointwise function of and with the square root, this operator is polynomial time computable. And in this R21 space, we could approximate it using the kind of piecewise constant functions and piecewise linear functions. These two kind of approximations, for each interval we calculate the average, but this piecewise constant approximation is not closed. This space is not closed under piecewise constant approximation, but it is closed under piecewise linear approximation. This one. And that was the L21 space and piecewise representation, and now I'm going to talk about the small L21 space and Fourier coefficient representation. So L21 is the space of sequences, the complex number of sequences such that they satisfy these two conditions. So this small L21 space is isometric to large L21, and the proof is by Parson-Burse identity. And we have this second condition, and we could use some additional argument to prove some related methods regarding this second condition. And Fourier coefficient representation is defined in a similar way that n, j, and k. N is the precision parameter, and j we need because this is not a string function but a string predicate, and k is just the index of the Fourier coefficient. The zk, this is the index of the Fourier coefficient. And because this small L21 space and large L21 space, they are isometric and they can be isometrically identified. Representation of one is a representation of the other. They can be considered the same space and vice versa. So this is the Fourier coefficient representation, and as I explained, and j encoded in binary, k encoded in yeah, and j encoded in unary, k encoded in binary. That's a typo. And with respect to and this Fourier coefficient representation has also linear modulus of continuity, and this is optimal by Steinberg's lemma. And our observation is that in Fourier representation, this functional of getting f and returning the integration from 0 to 1 is polynomial time computable, because this is just a matter of directly reading off from the encoding. And actually this computing the Fourier coefficient, this is the zeroth Fourier coefficient, and computing the Fourier coefficient is actually the characterization of or equivalent representations of this space, or representation delta is polynomial time reducible to Fourier coefficient representation if and only if delta makes polynomial time computable the functional this functional of computing the KAIST polynomial KAIST Fourier coefficient. And we have two conjectures. The first conjecture is that this functional is not polynomial time computable but exponential time computable under Fourier coefficient representation. And another conjecture is that given two functionals, the zeroth Fourier coefficient of this pointwise multiplication is not polynomial time computable but exponential time computable. The exponential time computation can be performed using the convolution and convolution. So I introduced you to small L21 space and its Fourier coefficient representation, and let me wrap up this talk and give you some perspective. This is the piecewise representation, and this is the Fourier coefficient representation I already introduced you. And we have this conjecture. This piecewise representation, this is functional. We have shown that this is not polynomial time computable with respect to piecewise representation, but we conjecture that this is polynomial time. I'm sorry, I'm confused. Anyway, this table describes the polynomial time computability or non-polynomial time computability of these two of these two functionals under these two representation. So this functional is not polynomial time computable under this representation, but is polynomial time computable under this representation, and something similar happens. It works the other way around for the other functional. But and this shows that these two representations are not polynomial time convertible to each other, because if these are polynomial time convertible, then one is polynomial time computable, then the other also has to be polynomial time computable. So computability, theoretically, these two representations have already shown to be computably equivalent, but our conjecture is that they are not, in a complexity theoretic viewpoint, they are not equivalent. So among these two non-polynomial time equivalent representation, the lesson is that we have to pick one appropriate representation according to depending on our purpose. The purpose will be which functionals or which operators do we want to compute in polynomial time, and depending on the purpose we need to pick one. And also future work, actually this is a work in progress. We also have to prove those conjectures more rigorously, and another future work is with respect to these spaces we get the Fourier coefficients. So what if we use another also normal basis, or then maybe we could this will characterize under some different basis we will have some different representation, and under this different representation maybe some other different kind of functionals will be computable, and different kind of operators will be computable. So we introduced the piecewise representation, and is there any functional that characterizes the piecewise representation, like in the standard representation of research function, or in the case of representation of Fourier coefficient representation? And if we combine two or more representation, maybe with respect to that representation, maybe we could compute more functionals in polynomial time, but this may destroy closure properties under operations. So this is the end of my talk. Thank you very much for your attention.
Thank you very much. Okay. Is there any questions or comments?